starting the recording. 7. This is the intro to what we're talking about with this crazy thing called the Shell method. In honor of my good old friend Eric Shell, I'm going to send him a tweet and say I thought of him today.
Who's Eric Shell?
Eric Shell is my great pals from high school. Eric Shell is doing fun things. Indiegogo. I'm advertising for you, Eric, in case you guys know Indiegogo. Have anybody heard of it? It's a money fundraising organization. That's his company. One of his, he and his buddy started that one up.
You skipped 6.
But Eric Shell was a math magician at its best. And he continues to be so. All right, volume of the solid formed by revolving the region about this region. Okay, here we go. You ready for this? Let's draw the picture. Pictures are pretty. X squared plus 1. X equals 1. Y-axis and x-axis. Y equals 0 and x equals 0. Cool? So the region that we're going to spin some way, it says about the y-axis. So it's about the y-axis, which means it's a dy. Kind of got those images in your brain? So I'm going to spin this way, about the y-axis. Okay. And then there's the region we're spinning. We're spinning that flap. Kind of like, imagine you're sitting in a vat of Jell-O, and you spin this flap. What does it carve out? You know? That would be bizarre, but kind of fun. Well, there you are. Spin it. And what we're interested in is finding I'm going to throw together, I can do the disk method for a while, but something funny happens. If I spin it around, I'm creating perpendicular disks. Remember, you're always perpendicular. Your slices, your cross-sectional slices, are perpendicular to the axis of rotation. So there's my disk. I drew it in there in blue. Crazy thing is I can only do that little disk, which, by the way, has a radius of 1 minus 0. So that's the outer edge minus the axis of rotation. Edge is x equals 1, and the rotation axis is 0. And if I take that, by the way, how many squares am I going to put in there? I stuttered. Hang on. There we go. So it's 1 minus 0 squared. That's our radius. We're using the disk method. And then, if I keep going, I can only do that little formula until I hit y equals 1. Because check out what happens to my radius at that point. It's not 1 minus 0 anymore. It's not, the distance isn't 1 minus 0. It's 1 minus, that function. The distance is from the x equals 1 back to that curved parabola that I have there. So it changes. So I'm going to have to do 2 integrals in this situation because it's not the same radius being rotated, being squared and pied. So there's one of them. This one's good. I can do that from 0 to 1. For the rest of the way, the rest of that flap, from 1 to 2, remember we're doing dy, so those are y values from 1 to 2. And if you're wondering where my 2 comes from, remember x squared plus 1 hits x equals 1 at 2. If you put 1 into the function, you get out 2. Now you ready? That integral, can you imagine, what's that radius going to be? What's your outer edge minus your inner, or is it, this is that wash, there's a hole in there. That is not a disk. It's not rotated around the axis. It's not smooth back to the axis. It's going to be a washer. It has a hole in the middle. So it's going to be outer radius squared minus inner radius squared. Okay, so this is where the washer comes in, is where you have a gap between the axis of rotation and the region being rotated. There's a gap in there, and after rotation, it's like a hole in the middle. Okay, so the formula is outer radius squared, which is our x equals 1, minus inner radius squared, which is our quadratic that's in there. Okay. Watch this. So outer radius squared minus inner radius squared, which is our quadratic-y looking cube. And that's it. So you want to go back for a page. Keep going. You go back one page. There is a lovely formula on the bottom of your sheet. I hope it made it. Where is it? Oh, you guys have it on your sheet. Well, let's go for it. Got to find where it was with y'all. There we go. This is outer radius squared, big capital R, minus inner radius squared. And that is the washer method. It's outer radius squared, pi outer radius squared minus inner radius squared, which we kind of did in that last problem. You have to get, so you spin around the x equals 1, and then we subtract out what this inner curve makes, this edge right here. We cut that part out, and we have a hole in the middle. Okay, outer radius squared minus inner radius squared. And outer radius is x equals 1, and it's with respect to the outer radius is the distance. I should probably put in here, my outer radius is actually from 1 back to my axis of rotation, 0. That's not just regular 1, it's from getting 1 minus 0, so I didn't make it up. Okay, this is, that outer radius is 1 minus 0. Okay. The distance from that outer edge here back to the axis of rotation. That's 1 minus 0. The inner radius is that that edge curve quadratic-y kind of thing back to the axis of rotation, but you can't write it as x squared plus 1. No. You have to write it in terms of y, so you just have to solve for you have to just do that solving for x, so you get a function of y instead of a function of x. So it's plus or minus the square root of y minus 1. The plus or minus, well, it is the plus side. That right-hand side in the first quadrant is the plus square root of y minus 1. But when we square it, we don't care. So it actually doesn't matter. Okay.
Wait, I'm confused.
Pause. All right, back to recording. That was a really good pause. Ask for more. Those are good. Okay, so you cool with those outer radius squared minus inner radius squared? That in itself we have to practice. So don't, this is just getting it all back. We have to practice until it settles in. It takes a while. So I put those together, and what do you got? The volume of that crazy bibbidi-bobbidi-boo. It works. You can do it by hand, which we will, and I'll do it relatively quickly. You can do it in a calculator, and you'll get an answer. That's one way to do it. Shouldn't it be done more efficiently? Couldn't we just do it from one integral? Wouldn't you want to?
There's another way.
There's another way. There's always another way. So it turns out when we get to the end of all these rotation methods, this shell method has its place. But a lot of times you can do either two different washer and disk kind of combination methods, like we just did here, or we can do the shell method. And it doesn't matter as long as you're consistent and accurate. Let's finish this one off, by the way. Okay. I just simplified a little bit. Squaring that radical y minus 1 is just makes it y minus 1, and they just left it in parentheses.
1 minus 1 is 0.
The top one is just 1 squared, which is 1. The antiderivative is x. That's why it's just pi x. I'm going to put in 1 and 0.
Y, but okay. Right?
Thank you. Y. Okay. And then we'll simplify from there. Got the other one to be y. Weird. Oh, the x got back in there. No. Stupid x. There you go. There you are. 2 minus y. I just did that and then took the steps. I don't want to beat you guys up with some integration pieces, but this one should look nice. Put 2 in there, put 1 in there, subtract. We'll get 3 pi over 2 cubic units. It's growing. That's bigger than the other ones, right? So this little one right here, what food should this be? We've had Hershey's Kisses, we have Rolos, we have ham. This is our cup that holds our drink of choice, Kool-Aid. Sparkling Coke. You guys in your crush cans, these are awesome. Way to go. Thanks for bringing those to class. All right, let's roll. Let's try it again.
Go back, go back, go back.
Okay, I'll go back. Shall we to the next part? Shall we continue? Because we got to get to this perpendicular, or we got to do. Okay, we got to get to this. This is fun. Are you ready? Same thing, same issue. Draw the region. There it is. It's this flap, spun in Jello. Oh, we'll just spin it in Jello. And then, this is going to be the crazy part. You ready? All new. We just did this, but we're totally doing it a different way. Couldn't we do this with a singular integral? Yes. We just did it with adding two rotations together. We put a cylinder with a bowl on top of it. That's how we did it before. Now we're going to do it with one integral. And this is called, you might need like a separate sheet because this is called the shell method. Okay. And shells are crazy. Okay, same region, right? See that bowl? Isn't that nice? That's one of my better drawings of that particular region being spun. We're going to carve it up a different way. You got to watch this. This is super cool. We are going to build this as a series of concentric cans. Whoa. Check it out. Concentric cans. So you take, bless you. Put cans inside each other, and the height of the can is determined by the curvature of that function that's inside there. So concentric cans that build it up, but infinitely thin. So what it is like you could build this out of like thick sheet metal wrapped up like this. If you had a whole bunch of concentric rings of sheet metal to build this, it would look really cool looking down in this bowl. It would make a nice bowl, but you would see the edge of the sheet metal that is descending to make this. It'd be kind of a cool way to make it, right? Wrapping sheet metal repeatedly.
Yeah.
That'd be a very retro, neat-looking bowl. It would weigh a ton.
I just looked up a bunch of
And then
3D
when you
modeling
open it,
websites if you want.
Unless you sealed it, it would be, yeah. So again,
I found a bunch of 3D modeling websites you can do.
oh, it's amazing. They're pretty cool. I make a lot of money on the side doing that kind of thing.
There's K3D.
But I have stopped exercising, as I told you guys, so modeling has been out for a while.
Yeah. This is more mathematical modeling, so you might still be in.
Oh. Sorry. That was personal information. Let's move on.
Will you model?
No, I'm just kidding.
Oh.
Yeah, it would have been awesome. Yeah, no, that would be more like, you model? What? Are you kidding me? That would have been you're very polite. X squared plus 1 is the height. So, this is the crazy thing about these cylindrical cans. We're going to unroll that piece of sheet metal. Concentric rings of sheet metal, or concentric cans. That means a can inside a can inside a can inside a can inside a can until it builds the shape. Well, we're going to unroll them. Slice it. Somewhere you make a cut and unroll that piece, and that thickness of that sheet, I'm going to put it all together in one fell swoop, and this is missing a couple things. Okay. It's going too far. I'll go back. That one right there. I want you to see that. Do you guys see that's circumference that I just wrote up there? I'm going to pause here and show you a whole bunch.